In the beginning there is a silence, a hush so profound that even the faintest tremor of a distant star seems to reverberate through the void. In this silence, humanity finds itself adrift, a solitary consciousness awakening in the darkness, asking, almost timidly, what is real? This question has haunted philosophers and physicists alike, echoing through the marble corridors of Plato's academy and the humming laboratories of the 21st century. The notion that the world might be an elaborate illusion is ancient, but in our age of quantum computers and sprawling digital landscapes, it has taken on a new, electrifying urgency. Among the most audacious proposals is the simulation hypothesis, the idea that everything we perceive, from the swirl of galaxies to the warmth of a loved one's touch, might be the output of a vast cosmic computation, conjured into being by entities as far beyond us as we are beyond the simplest protozoan. The roots of this hypothesis stretch deep into the soil of human wonder. It is not born solely of modern science, nor is it a mere byproduct of our digital age. It is the latest blossom on a philosophical branch that has grown since antiquity. Plato's Allegory of the Cave, with its prisoners mistaking shadows for reality, is its earliest ancestor. In the 17th century, René Descartes wondered if an evil demon might be deceiving him, orchestrating all his senses to fabricate a world that did not exist. These were metaphors, allegories for the limits of perception and the longing for certainty. But as silicon circuits began to mimic the firing of neurons, the metaphor began to shimmer with a new technological plausibility. The simulation hypothesis was articulated with scientific clarity by the Swedish philosopher Nick Bostrom in his 2003 paper, Are You Living in a Computer Simulation? Bostrom's argument unfurled not as a fevered speculation, but as a logical trilemma. If advanced civilizations arise and develop immense computational power, and if they are interested in running ancestor simulations, detailed recreations of their own evolutionary history, then, statistically, simulated minds would vastly outnumber biological ones. It becomes, in Bostrom's calculus, overwhelmingly likely that we are one of the simulated, not the simulators. The question is transformed from idle speculation to a matter of probability, a roll of cosmic dice. Yet, as the idea seeps from philosophy into the hard, cold light of physics, a new breed of evidence is demanded. Scientists, after all, are trained to distrust the merely plausible. They seek the measurable, the testable, the repeatable. And so, across continents and decades, a handful of physicists and cosmologists have begun to ask, if the universe is a simulation, might it leave fingerprints, tiny glitches, artifacts of code, or telltale patterns, etched into the fabric of reality itself? The first avenue of inquiry leads us to the quantum world, a theater so strange it seems already designed by a trickster intelligence. Here, particles flicker in and out of existence, information is preserved in ways that defy common sense, and measurement itself seems to conjure reality into being. Among the phenomena most often cited is the fundamental discreteness of the universe at the Planck scale. In 1899, Max Planck proposed that energy is quantized, coming in discrete packets rather than a smooth continuum. This granularity persists throughout physics. Space, time, energy, and even information all seem to be pixelated at the smallest scales, as if the universe were running on a digital substrate. Physicist John Archibald Wheeler, in his famous it from bit formulation, suggested that information is the most fundamental ingredient of reality. The bits of the universe, not particles or fields, constitute its real substrate. Wheeler's vision was bold, poetic. Every physical quantity, every quark and photon, arises from the yes-no questions of binary logic, the coin flips of cosmic computation. Quantum mechanics, with its superpositions and entanglements, seems to function not unlike a quantum computer, a device capable of calculating all possible realities at once, collapsing them into a single outcome only when observed. This peculiar feature, the so-called observer effect, has led some to speculate that the universe is rendered in real time, like the polygons of a video game materializing only when the player turns their gaze. But these are metaphors, not measurements. Is there then any experimental evidence, any hard data, that points toward our world being a simulation? Here the search becomes fraught, for the boundaries between simulation and reality are, by design, subtle and elusive. Nevertheless, some physicists have proposed ingenious tests. One of the most compelling comes from Silas Bean and his colleagues at the University of Washington. In a 2012 paper, they proposed that if our universe were simulated on a lattice, analogous to the way physicists use lattice quantum chromodynamics to simulate subatomic particles, then certain artifacts would leak into our measurements. In particular, the highest energy cosmic rays, particles that zip through space at nearly the speed of light, should exhibit anomalies as they approach the resolution limit of the underlying grid. If the simulation's lattice spacing is at the Planck length, then cosmic rays with energies above a certain threshold should behave strangely, their trajectories subtly altered by the granularity. To date, no such anomalies have been definitively observed, but the search continues as detectors grow more sensitive and cosmic rays more thoroughly catalogued. Another tantalizing clue emerges from the study of black holes and the paradoxes they generate. In the 1970s, Stephen Hawking showed that black holes radiate energy and eventually evaporate, a discovery that unleashed a crisis in theoretical physics. If information is destroyed in this process, as Hawking's equation suggested, then the most basic tenet of quantum mechanics is violated. In the decades since, the consensus has shifted. Information, it seems, is preserved, albeit in ways that are deeply mysterious. The so-called holographic principle, proposed by Gerard 't Hooft and Leonard Susskind, posits that all the information contained within a volume of space can be encoded on its boundary, like a hologram. This principle is not just a curious metaphor. It is mathematically rigorous, supported by calculations in string theory and the physics of black holes. Our three-dimensional universe, according to this view, may be a projection from a two-dimensional surface, a kind of cosmic hard drive, encoding every event, every thought, every breath. The holographic principle dovetails eerily with the simulation hypothesis, suggesting that our reality may be emergent, rendered from data inscribed on a boundary beyond our perception. In 2017, a team led by Craig Hogan at the Fermi National Accelerator Laboratory constructed the holometer, a device designed to detect the quantum jitter of space itself, subtle fluctuations that would betray the universe's underlying discreteness. Though the holometer detected no definitive evidence of holographic noise, its null result is itself a clue, narrowing the parameters within which a simulation might operate. The quantum world offers further mysteries. The phenomenon of quantum entanglement, in which particles separated by vast distances seem to share information instantaneously, defies classical explanations. In 2019, a team led by John Bell's intellectual heirs, physicists at the University of Vienna and MIT, performed the most rigorous loophole-free Bell test to date, confirming that nature violates local realism. The universe does not behave as a local deterministic machine. Instead, correlations exist that seem to transcend space-time. Some theorists, such as Seth Lloyd and David Deutsch, interpret these phenomena as evidence that the universe is itself a quantum computer, processing information non-locally, outside the bounds of classical causality. Yet for all these hints, the simulation hypothesis remains, for many physicists, a speculation, intriguing, provocative, but lacking the ironclad evidence that marks the greatest scientific revolutions. Theoretical physicist Sabine Hossenfelder has argued that the hypothesis, while logically consistent, is unfalsifiable under current technological constraints. If the simulators are sufficiently advanced, they could mask any glitches, patch any errors, and ensure that the simulation remains, for all practical purposes, indistinguishable from reality. Neil deGrasse Tyson, the astrophysicist and science communicator, has estimated the probability that we are living in a simulation as better than 50-50. Yet he acknowledges that this is a statement of philosophical inclination, rather than empirical fact. Others, like the physicist Max Tegmark, take a more nuanced view. Tegmark, whose mathematical universe hypothesis posits that reality is not merely described by mathematics, but is mathematics, suggests that the distinction between simulation and reality may be meaningless. If our world is governed by mathematical laws, and those laws can be instantiated on a computer, then the substrate, carbon, silicon, or something else, is irrelevant. The realness of our universe is a question of structure, not substance. Nevertheless, the search for evidence continues, propelled by the insatiable curiosity of the human mind. One line of inquiry focuses on the so-called fine-tuning of the universe, the physical constants that govern our cosmos, the strength of gravity, the charge of the electron, the cosmological constant, are set with uncanny precision. A slight deviation in any of these values, and the universe as we know it would be lifeless, sterile, or simply impossible. Some see in this fine-tuning the hand of a designer, others the statistical inevitability of the multiverse. But to the proponents of the simulation hypothesis, it suggests something else. The parameters have been set as one would configure the rules of a game, calibrated for complexity, beauty, and the emergence of consciousness. In 2020, a team of researchers led by Zohar Ringel and Dmitry Kovrizhin at the University of Oxford explored the computational complexity of quantum systems. They showed that simulating even a small patch of quantum matter on a classical computer quickly becomes intractable, requiring resources that grow exponentially with system size. This raises a paradox. If our universe is a simulation, how do the simulators manage the computational load? One possibility is that the simulation is lazy, rendering only those aspects of reality that are observed, much as a video game loads textures only in the player's field of view. This idea is not far-fetched. It is the basis for many optimizations in modern computer graphics and virtual reality. If true, it might explain certain quantum phenomena, such as wave function collapse, as the universe calculating outcomes only when demanded by an observer. But here, the evidence grows thin and the speculation thickens. For every experiment designed to catch the universe in a lie, there is a counter-argument. The simulation may be perfect, the code unbreakable, the architects unknowable. The search is not in vain, for it brings us to the edge of physics, where theory and philosophy intertwine, and the very nature of existence is questioned. What then do the leading voices in physics say? The field is divided, as it often is when the questions are most profound. David Chalmers, the philosopher of mind, has argued that simulated worlds can be as real as physical ones, provided the experience is indistinguishable. He points out that consciousness, whatever its substrate, is substrate independent. If a mind can emerge from neurons, it can emerge from code. Elon Musk, the entrepreneur, has famously wagered that the odds that we are in base reality are 1 in billions, citing the rapid progress of video game graphics and virtual reality as evidence that ancestor simulations are not only possible, but inevitable. Yet for every Musk there is a Roger Penrose, the Nobel laureate, who maintains that consciousness is rooted in quantum gravity, irreducible to computation. Penrose's orchestrated objective reduction theory posits that the mind is not a mere algorithm, but something fundamentally new, arising from the collapse of quantum states within the microtubules of neurons. If Penrose is right, then no simulation, no matter how powerful, can capture the essence of consciousness. The debate is not merely academic. The implications of the simulation hypothesis for humanity are profound, unsettling, and potentially exhilarating. If we are living in a simulation, then the traditional boundaries between science and religion, between physics and metaphysics, are blurred. The ancient question, who created us and why, takes on a technological twist. The simulators, if they exist, might be scientists, artists, or even curious children in another universe. Our moral and existential frameworks are thrown into question. Do the simulators intervene in our world? Do they watch, judge, or care? Are there ethical obligations owed to simulated beings? Are we, ourselves, the architects of future simulations, destined to become the creators of new realities? Some philosophers, like David J. Chalmers in his 2022 book, Reality Plus Virtual Worlds and the Problems of Philosophy, argue that simulated lives have meaning, that love, beauty, and suffering are no less real in a simulation than in base reality. Others, like the physicist Frank Wilczek, are skeptical, insisting that the universe's elegance and coherence point to a reality more profound than any digital code. The search for evidence continues, not only in the laboratories of physics, but in the code of consciousness itself. Could déjà vu, synchronicity, or the strange patterns of dreams be artifacts of a simulated mind? Are the uncanny mathematical coincidences, the Fibonacci spiral in sunflowers, the golden ratio in galaxies, hints of a designer's aesthetic sensibility? Or are they the inevitable byproducts of a universe governed by mathematics, whether simulated or not? In the end, the simulation hypothesis confronts us with the limits of knowledge, the horizon beyond which science blurs into poetry. The strongest evidence is circumstantial, the experiments ingenious but inconclusive. The universe remains stubbornly enigmatic, revealing just enough to tantalize, never enough to satisfy. The mystery is not a failure, but a gift, a reminder that we are, all of us, explorers on the edge of understanding, peering into the darkness with hope and wonder. And so, as the sun sets on another day in this world, real or simulated, we are left with questions that shimmer in the twilight. What does it mean to be real? Who, if anyone, watches from beyond the code? If the universe is a simulation, does it matter? Or is the search for meaning, the longing for truth, itself the highest expression of what it means to exist? The journey is not over. New experiments are being devised. Quantum computers are probing the limits of computation. Astronomers are mapping the cosmic microwave background for statistical anomalies, and philosophers are inventing new languages to capture the strangeness of being. Each step brings us closer to an answer, or perhaps to a deeper, more beautiful mystery. In the silence that follows, there is a sense of awe. The universe, whatever its nature, is a work of staggering complexity and beauty. Whether it is the product of mindless laws, a cosmic artist, or a team of higher beings, it is, for us, the only reality we know, and in the end, that may be enough. For to seek, to question, to wonder, these are the marks of consciousness, simulated or not. And in that search we find ourselves alone together, dreaming within the dream.